Okay, good morning, everyone. How did the homework go? Do you have any questions about the homework? Please get started. Okay, anybody has any questions? All right. Okay, so I'm going to do two problems from the previous section. Actually, we're going to work the whole hour on the same section. So first, I would like to do two problems to contrast two ideas, and then I will proceed. And if you have any questions, please feel free to put them on bright space. So I will do number 15. Sorry, I meant number 5. And then I will do number 19 because there is some kind of relation between them that I would like it to be clear. So number 5. So the question that they gave us is system. Plus x3 equal to 0. And then they gave us minus 4x1 minus 9x2 plus 2x3 equal to 0. And finally, minus 3x2 minus 6x3 equal to 0. And the question is to solve the system and write the solution in parametric vector form. So first, solving the system is the same thing as solving the following vector matrix equation. So that's 0, 0. I always rewrite it so you guys see the relationship. Okay. So that's a 1, 3, 1, minus 4, minus 9, 2, 0, minus 3, minus 6, and that's the vector. Okay, so we are gonna solve it. Sorry, I'm trying to adjust a little bit, hoping it will be clearer. Yeah, so we solve it always the regular way. That's my vector here, 1, 3, 1, minus 4, minus 9, 2, 0, minus 3, minus 6. And that's give me 1, 3, 1, 4, 4 times 3, 12, minus 9, 3. And this is 4, 4 plus 2, that's gonna give me a 6. 0, minus 3, minus 6. Okay, and one more operation, almost. 1, 3, 1, 0, 0. And if you guys do two operations in your mind, you will get, actually, I will do it one by one, 0, 0, 0. Okay, and so this is my leading here, and this is a leading. I can stop here, or I can go one more step, and then I will have the following. 1, 3, 1, 0, 0, 1, 2, 0, 0, 0, 0. So we're almost at the reduced echelon. The last row, and immediately we know that we have a free variable in here. So that's homogeneous, so the solution exists. Minus 3 plus 3, it's a 0. Minus 6 plus 1, it is a minus 5. All right, so this would give me immediately x3 is a free variable. The second equation will give me x2 is minus 2x3. And the first one will give me x1 is 5x3. Okay, so in vector form, in parametric vector form, which was the new idea last time, we set x3 equal to t. And this would give me x1 is 5t, x2 minus 2t, x3 is t. So in parametric vector form, x could be written as. And then we figured out we times 1. So that's what we call the parametric vector form of the solution. It means every solution, every x1, x2, x3 that solve the system is a scalar multiple of the vector 5 minus 2, 1. And last time we described this geometrically as follows. 0 is absolutely a solution because I set t equal to 0, and every other solution is a scalar multiple of 5 minus 2, 1. Means if I take the vector 5, a little bit minus 2, 1, which is somewhere, put me in here, then every solution is actually on this line because it is every solution you take this vector and you scale it. So let me draw, so this line here, you can visualize this as the solution of AX equal to 0. This is a solution, twice is a solution, minus is a solution, everything here is a solution. Okay. Number 17, I will do it because I want to contrast it with this problem. So number 17 is the following. I'll write it, and at every step, I'll see the connection between number 19 and this problem. So I'll keep this problem in front of us, and I will do number 19. So number 19 is the following. x1 plus 3x2 plus x3 equal to 1, minus 4x1 minus 9x2 plus 2x3 is minus 1, and finally minus 3x2 minus 6x3 equal to minus 3. So if we compare it exactly with number 5, the coefficient part, the equation are the same, it's only the augmented part which is changing. So the question is, what happened? What's the relationship between the solution of that and the solution of this? So this is x1, x2, x3, and 1, 3, 1, minus 4, minus 9, 2, 0, minus 3, and minus 6. So as you realize, coefficient is the same. As I share the same coefficient matrix, is the augmented term. That's a 0, and that's another one. So here the possibility will be either the system will not have a solution, or if it has, the question is there any relationship between the two solutions? So we solve exactly the same. So watch what's happening when we solve. 1, 3, 1. This one, we have a 1 here. Minus 4, minus 9, 2, minus 1, 0, minus 3, minus 6, and 3. What I want you to notice is that the row operation that I performed here exactly will be performed here. So when I'm going to perform the row operation, I will perform the same thing. Nothing is changed in terms of the row operation. I will have 1, 3, 1, 1, 4 minus 4, 0, 3, 6. The only thing that's changing is the augmented term. Here I have a 0, and this is definitely not going to be a 0. That's going to be 4 minus 1, which is a 3. So the operation are the same. So this piece will just remain the same. It's only the augmented term that's changing every time. 0, 0, 0, minus 3, minus 6. This is the term that's going to change. In this case, because it says 4 plus 3, that's going to give me a 7 up here. 4 plus 3, that gives me a 7. So that's a minus 3 here. That's why I'm panicking. So that's a minus 3 here. 4 minus 3 Sorry, that's remain minus 3. Okay, so everything remained the same. So we can keep going. We will perform exactly same operation. And if we guys do all the way to the reduced echelon form, we're gonna have the following. 1, 3, 1, 0, minus 5. This piece will remain the same as here. 0, 1, 2, 0, 0, 0 is the augmented form that will change. And if we do the math, we get 2, 1, 0. So this remain, the reduced echelon form here is the same as the previous one. This one will change. Now, how the solution will be affected? So x3 is going to be free in both situations. What about x2? This row would tell me that x2 is 1 minus to x3. So x2 will be 1 minus to x3. x1 is going to be 2 plus 5x3. So I'm trying to build the relationship between here and here. But in the homogeneous setting, x3 was free, x1 is 1 minus 2x3, x1 is 2 plus 5x3. So this piece is basically remained the same in the homogeneous, non-homogeneous, but we're adding it to. So now when you write this in vector equation, I put x3 to be a t. And finally, my solution would be x equal 2 plus 5t, 1 minus 2t, and t. And the way we write this in parametric, the 2 in x1 is negative. This one, yes, you're right. I copied it wrongly. You're absolutely correct. Thanks, Celine. All right. So this is going to give me the following. Write it in vector 4. I'm going to write the 5t minus 2t and t plus minus 2, 1, 0. So in vector form, this is going to be equal to t times 5 minus 2, 1 plus the vector minus 2, 1, and 0. Okay. So let us see the relationship between this and the homogeneous system. That's the homogeneous system. Every solution is a scalar multiple of 5 minus 2, 1. If you keep the same augmented matrix, but the coefficient matrix, you keep it the same, but you change the augmented term, the solution, this piece of the solution is the same, but you're always adding this special vector minus 2, 1, 0. So geometrically, what's going to be the relationship between the two solutions? So geometrically, what's really happening? I will keep this in front of us, and I'll draw back and see the relationship between the solution of AX equal to 0 and AX equal to B. First, I draw AX equal to 0. AX equal to 0, this is the vector 5 minus 2, 1, and the solution was this line. That's AX equal to 0. When I kept the same coefficient matrix, but I changed the augmented term, what is the solution? We talked about this at the end of the lecture. Every solution is obtained like this. If I take t equal to 0, I get the vector minus 2, 1, 0. So minus 2, somewhere in the back, 1, 0. Let us assume that is right here. That's a solution. Then any other solution is obtained as follows. If you take 5 minus 2, 1, you scale it, and then you add the vector 5 minus 2, 0. You scale it, and you add 5 minus 2, 0. So every other solution is going to be on the line. So this is going to be the solution of AX equal to B. So the solution of AX equal to B is going to be the line, which is pass through -2, 1, 0. That's going to be the point on the line, and in the direction of 5, -2, 1. So that's going to be the direction, and that's going to be the point. And geometrically, the solution of Ax equal to 0 and the solution of Ax equal to b are, at least are 3 parallel to each other. That's the homogeneous and that's the non-homogeneous system. So that's the relationship between the two solutions. So in general, we can state the following theorem. So suppose Ax equal to b is consistent. Consistent. And P, a particular solution. It means a solution obtained for a specific value of T. So a particular solution here is -2, 1, 0. That's a special solution. And P, a particular solution of X equal to B. Then, every other solution has the following form. X equal to B is of the form. Every other solution is the particular solution P and another solution of the homogeneous system. So it could be written VH plus P, where VH is solution of the homogeneous system, Ax equal to 0. It means if you keep the coefficient matrix the same, the augmented matrix, so you solve the homogeneous X equal to 0, the same coefficient, but you put a vector B, we're creating a whole new system. But because what's the relationship between those two solutions is that every solution of Ax equal to B is a certain particular solution, and you add to it a solution of the homogeneous system. So it means you take this one and you add a scalar multiple of the homogeneous, and you add a scalar multiple of the solution of the homogeneous. Right, so the last question we will do before we start ideas is the following. I want to solve one more problem and then we proceed. So let us solve just to make sure we understand parametric equation fully. X1 plus 3x2 plus 5x3 plus 4x4 equal -1, and x1 plus 2x2 plus 2x3 plus x4 equal to 4. And the question is for us now not solving, but write the solution in parametric vector form. So first, I would like always to remind you how to write it as a matrix equation. That's 1, 3, 5, 4, x1, x2, x3, x4. And this is B, which is -1, 4. And 1, 2, 2, 1. Okay, that's a matrix form. All right, so let us solve it. And I will give you the echelon form immediately so we can solve quickly. All right, we can reduce. And if we row reduce, we get the following. 1, 0, 4, -5, 4, 0, 1, 3, 3, 6. All right, so now we're going to solve and write the solution. So x2 and x1 are basic, and x3, x4 are free. So now we are going to write the general solution. Free and free. The second row, give me the following. X2 equal 6 minus 3x3 minus 3x4. The first row, give me x1 equal 4 minus 4x3 plus 5x4. Okay. Now in parametric vector form. Now we have two free variables. I set one equal s and one equal to t. And my solution become x1, x2, x3, x4. 4 minus 4s plus 5t. 6 minus 3s minus 3t, s and t. You can use any name you want for the free variable. So finally, this will give me the following. As we did last time, we cannot factor anything. We're going to have two parameters hanging in there, and we're going to have a constant term. So now we're going to have a 4 minus 5 and a 5 is 6 minus 3 minus 3. I only have s here, so it have to be a 0. This have to be 1. This have to be a 0. This 0, and this is 1. And that's the solution in parametric vector. Any questions? Now what we're going to talk about is the following. A lot of things we talk about today is you should be able to help me with it because it's we've seen it somehow. So on the uniqueness of the solution of Ax equal to b. One of the questions we will be asking, especially starting in the following section, in section 1.6, is the solution unique? Is the solution infinite? That's going to play an important role for us. So let us establish few facts when we can say that the solution is unique. So on the uniqueness, of the solution of Ax equal to b. Okay. So when is a solution unique? Can anybody kind of think about the answer? When can we guarantee that the solution is unique? What should we know about the coefficient matrix to guarantee the uniqueness of the solution? Okay, let me note something. Suppose I have a matrix A. A matrix A. 1, 2, 3, 1, minus 1, 2, 0, 3, 3. Just any matrix. And I reduce it. 1, 2, 3, 0, let us say minus 3, 2, 0, 3, 3, and then I reduce it. 1, 2, 3, 0, minus 3, 2, 0, 0, 5. Okay, I'm going to call this U. U stands for the echelon form. Exactly. Now, if I take A and I augment it. As I mentioned a little bit at the beginning of the lecture, so 1, 2, 3, 0, minus 1, 2, 0, 3, 3, and this is my vector B. What's going to happen when we augment? So let me call this B1, B2, B3. This piece, the row operation are not going to change. So what's going to happen is the following. The same row operation, so we're going to have exactly the same matrix. What's going to change is this vector. This vector is going to change in the operation. So this will going to remain B1, for example. This is going to be minus B1 plus B2. And this is going to be B3. This not change, this vector change. So I can do one more time. This piece will remain the same. And this one will change. And let us call it D1, D2, and D3. It'll change into a vector D. All right, so this means that if A, the matrix coefficient A, is rho equivalent to U, then if I add a term, this is going to be rho equivalent. A will be turned to U, and B would turn to something, to a certain vector D. But the coefficient part will not change. So now this will tell me on the uniqueness, and that's what your classmate wrote on the board. Okay. Uniqueness. Of the solution. Okay, says the following. If a matrix, so matrix A has a pivot in every column, so if you have a pivot in every column, it means when you reduce, you have a leading in every column, then the solution of the system AX equal to B is unique. Of course, under the condition, if AX equal to B is consistent. If it's not consistent, we don't care about anything. It's consistent, okay? So if the matrix A has a pivot in every column, pivot in every column means the echelon form has a leading in every column. If this happens, then the solution will be always unique, because if you have a pivot in every column, all the variable will be basic, we will have no free variable. So that will guarantee the uniqueness. So pivot in every column always guarantee the uniqueness of the solution. And the reason is, as your classmate said, pivot in every column tells me that no free variable. Okay. So the number of pivot tells me whether the solution is unique or not. Right. Part 2 is on the existence of the solution. So we're going to talk a little bit about the uniqueness and the existence. So question number 2 is on the existence of the solution. Existence of the solution. All right. So I will set up the question for you. Suppose A matrix. And you're told that A has a pivot. It means the echelon form has a leading. That's what I mean, has a pivot in every row. So we talk columns and rows. So now suppose in every row, does AX equal to B has a solution, regardless what B is? Yes or no? So suppose you have a matrix and the coefficient has a pivot in every row? Can we guarantee that the system has a solution for all B? I want you to imagine a picture in your mind a little bit before we discuss this. Usually when I work with matrices, I imagine picture. It helps me. So on the side, what I am telling you. I'm telling you that A, it means the coefficient matrix, watch carefully, the coefficient matrix, this piece, has a pivot in every row. Means, suppose it's a 3 by 4, just to make things easy for us. Suppose it's a 3 by 4. I have a pivot in this row. I have a pivot in this row. And let us say I have a pivot in that row. So, and I have a bunch of stuff here. All right, I want you to look at the picture now. Can we say that regardless what I plop in here, I will have a solution? I want you to look at it one more time. Some students are changing their mind. Anybody else? I have answer from Pedro. I have an answer from Haley. They both tell me yes. Does anybody else agree with them? Absolutely, it is yes. Okay, because if I have a pivot in every row, in the coefficient matrix, remember A is the coefficient matrix. If I have a pivot in every row of the coefficient matrix, mean there is no way I'm going to have a pivot in the augmented term. It means I will never have the scenario 0, 0, 0, 0 in non-zero term. So we definitely have a solution for all B. So if the coefficient matrix, as you realize, all my condition now on the coefficient matrix. So the first one tells me if the coefficient has a pivot in every column, then the solution is unique once we have a solution. Now I'm talking about the coefficient having a pivot in every row, and I'm telling you that it has a solution for all B. So the answer is yes, because A, if I take the matrix A and I put B, any vector B in it, when I reduce, I'm going to have this is going to turn to a vector U, to a matrix U, and B will turn something. I don't know what it turned to, but it turned to a something, which is a vector D. Now, since U has a pivot, since U has a leading in every row, U, that's the coefficient. It means we have no row of the form. Means AB, when reduced, will have no row of the form. Okay, since U has a leading in every row, it means that AB, when reduced, will have no row of the form 0, 0, where this is not 0. There is no way this scenario can occur because we have a leading in this row. And every row has one leading. So the leading has to be right here. So we have this cannot occur. So this leads me to the second idea here, which says the following. If a matrix A has a pivot in every row, then the system AX equal B is consistent for all B. Means if you are solving the system, regardless what you put to the right side, whatever you put, whatever constant term, you will find a solution. And it's going to mean something else that we'll get to it when I'm done with that. Mean that every vector B is going to be in the span of the columns of A, which is a remark I'll have to make by the end of the discussion. All right. So every A has a pivot every column, guarantee the uniqueness if we have consistency. For the existence, if A has a pivot in every row, then we always have a solution. Okay. So now the question is, what happens if we don't have a pivot in every row? So the question is, what happened if we don't have a pivot in every row? Okay, so if you have a pivot, it means regardless the B is, whatever I plug in for B, anything, we have a solution. What happens if we don't have this luxury of a pivot in every row? So I will elaborate this by an example, and then we will see what the rule is. So suppose I have the following matrix A, and this is 1, -1, 2. So I usually take easy matrices. And 2, 0, 2. So I'll explain, as I said, the picture by an example. -1 and 4. Okay, that's my matrix A. And the question is, let B be a vector B1, B2, B3. And the question is, under what condition? Under what condition? On the entries of B. Under what condition? On the entries of will the system AX equal to B has a solution. It means what should B1, B2, B3 satisfy for the system to have a solution? All right, the only way we can answer this question is we have to solve. And then ask ourselves is, okay, what's really going on? Can I solve for every B, or there are conditions that we have to have? Okay, so we solve. So we set up A, B, and we solve. 1, 2, 3, B1, and -1, 0, -1, B2, 2, 2, 4, and B3. Okay. And I will reduce because I have no idea what condition those should satisfy for us to have a solution. So we solve. And whenever we're solving and we have parameter or number that we don't know in the augmented part, we only go to the echelon form. You never go to the reduced echelon form because it becomes really more complicated. So whenever we're trying to solve or we're trying to discuss the solution, then you'd stop always at the echelon form. So let's do that. I usually try to pick my matrices easy, so to elaborate the idea only. So this will give me the following. 1 minus 1, give me a 1, a 2, a 3, and a B1. 1, I will have to add the first row, 0, 2. 2, I'm adding them. So it will give me B1 plus B2. And then here, -2 plus 2, it's a 0. -2, that's a -2. -6 plus 4, a -2. And this would give me -2 B1 plus the B3. As I said, we hit the echelon form and then we produce. So we haven't hit the echelon form yet. So one more step, I think. So I'm going to add row 2 to row 3. And then I will have 1, 2, 3. That's my B1, 0, 2, 2, B1 plus B2, 0, 0, 0. I'm adding those two. So if I add them, I will have B1 minus 2B1. That would give me minus B1 plus B2 plus B3. Okay, so that's a situation where the matrix A, that's A, when we reduced it, we have a row of 0. Okay, so that's the scenario I am working with. So now my question addressed to you is, when is the system consistent? Under what condition on the entries of B will the system has a solution? Very quickly. Absolutely. The system will have the solution only when this up here is equal to 0. So when minus B1, so not every vector will give me a solution. That's the condition that I have to satisfy. So the minute I have a row of 0, when I'm starting with the B1, B2, B3, it's going to change. And it gets me to a certain vector here. And that's really where my issue is going to come. I will have solution when this relationship between the B1 equal to 0. So now very, very simply, I'll ask you the following trivial question is, find a vector B such that Ax equal to B is consistent. Okay. And then I want you to give me a B such that Ax equal to B is inconsistent. All right. All right, so quickly give me the first vector. Give me a B so that if I plug it in here, if I plug it in the equation, Ax equal to B, I will have a solution. There are a lot of them, I want one. 2, 1, 1. Okay, I will write it and I will see if your classmate is correct. He gave me the vector 2, 1, 1. So does it satisfy this condition? So minus 2 plus 1 equal to 0. It means I check that. Okay, satisfy the system is consistent. Okay, yeah. So it means here, what does it mean for you? It means if you are solving the system Ax equal to 1, 1, then what's happening? You're going to have a 0 in here and you're going to have infinitely many solutions. The system will be consistent. And now give me a vector B such that Ax equal to B is inconsistent. It's an easy question. All of you can answer that. Give me a vector B such that the system is inconsistent. Quickly. 0, 0, 1. We don't have to have 0, 0, 1. Give me something where the last component is 0. It doesn't have to be 0, 0, 1. Give me one where the last component is 0. And that's the relation that, sorry. Okay, minus 3, 4, 0. Okay, this doesn't have to be 1. Absolutely not. Let me take that. Then this will be equal minus 3 plus 4 plus 0. This is equal to 1, different from 0. The system is inconsistent. Because what's happening here, if I put minus 3 here, what your classmate gave me, I put 4 here, and I put 0 here, this vector, and I start doing operation, I'm going to have a 1 in here. And this is going to be the B1 plus B2. This is going to be the B1 plus B2 that she gave us, and this is going to be minus 3. So if I do those operations, I will get minus 3, 1, 1, hence an inconsistency in the system. Okay. So what does this tell us? What does this tell us? So if I get A, the matrix A, and I ended up with a row, so A has a row that has no pivot, it means has no leading, the scenario would be that for some vector B, there will be a solution. And for some vector, the system will be inconsistent. So we don't have solution for all B's. We don't have inconsistency for all B's. So in this scenario, the following happen. Okay. If A, the coefficient matrix, does not have a pivot in every row. Remember, all our conditions are on the coefficient. Then we have the following. For some B, for some vector B, Ax equal to B is consistent. So we have some vectors for which we have consistency. And for some vector B, we have inconsistency. It means not every vector guarantees consistency of the system. So I elaborated this by an example. I can give you a kind of a general reason why it happened. Generally, the reason is, even though, is the following. Suppose you take AB here, okay, and let us say we reduce it. At the end, we're going to have add to something, and this is a D. So B is going to change to a certain vector, and A is going to be reduced by that. So the idea that if I take the last vector, if I take D to be the vector 1 at the end, okay, suppose I take D to be this vector, then if I reverse the row operation, so by reversing the row operation, so take D to be the vector 1 at the end, and I don't care about anything else, then by reversing the row operation, so that's the theoretical reason, we can find a vector B. So if I reverse them, we can find B such that AB is row equivalent to U, D, where UD, where the last row of UD is gonna be 0, 0, etc., 1. So in general, if you want to generalize, I mean, the example show you exactly what's happening. If you want to make it a more theoretical reasoning, you take AB and you reduce it, you get U and something else, because B will change. If I pick this something else to be 1 at the end, and then I try reversing the operation I did, I can go back and find a B, so that AB will be row equivalent to UD. But this special D will make the last row of this augmented to be 0, 0, 0, 1. So that's really theoretically what's happening. So now I will ask several questions, not a lot of them, to kind of sum up all those ideas. So here are my questions. None of them is hard if you understood what I said. So summary of what we did. Summary is conclusion. Suppose A is the coefficient matrix. Then uniqueness. If A has a pivot in every column, and AX equal to B is consistent, then the solution is unique. Then solution unique. Try to understand more than memorize. Because we have no free variable in this scenario. Existence. Okay. If A has a pivot in every row, then AX equal to B, consistent for all B. Regardless what you put in here, I can find a solution. Okay. No pivot in every row, then anything can happen in the following sense. In every row, then for some B, system consistent, and for some, the system is inconsistent. Okay, so that's really the effect of the matrix itself on the coefficient matrix on the solution of the system. So let me give you some questions. Question number 1 is, okay, suppose A, a 4x3 matrix. So questions. So A is 4x3. Already you should have a picture in your mind. What is it? And A has 3 pivot. It means when you reduce it, the echelon form will have 3 leading. Question. Does the system, the homogeneous system, AX equal to 0? That's homogeneous. So there is no consistency issue because it's homogeneous. That's the homogeneous system AX equal to has a unique or infinitely many solution. Question number 1. So the homogeneous system, does it have a unique or infinitely many solution? What can you say? Unique. Pedro say unique because A is 4x3. So let us start thinking in our mind. Draw the picture. Draw always the picture. So A is 4. It means it's 4 rows and 3 columns. That's really my A. It has 3 pivot. So if it has 3 pivot, it means at the 3 column, it means we have to have a pivot in every column. Okay? And of course, the last column will have to be 0. Now, is the solution unique? Absolutely, because you have a pivot in every column. I don't care about the last what's happening at the last row, because this is AX equal to 0. So basically, this is 0, 0, 0, 0. So the system is consistent. Since I have a pivot in every column, so first note, AX equal to 0 is consistent. 0 is a solution. Now, since we have a pivot in every column, that's a 4x3. It means no free variable. Just to remind you what this means. Hence, solution is unique. It's unique. Okay. So you have a matrix X with AX equal to 0. You have a matrix A. You reduce it. You get 3 pivot. It means AX equal to 0 will always have a unique solution. All right. Question number 2 here. is, does AX equal to B? It's the same matrix. Has a solution. For all B. Means we always find a solution. A is the same matrix. It's a 4x3 with 3 pivot. Does AX equal to B has a solution for all B? Always draw the picture in front of you. So my A is 3, 4, 3. Okay, so it has 3 pivot. It means that's the picture here. That's for A. So that's my A piece. So that's the echelon form of A right here. So it is a 0. We have a pivot. Anything. 0. We have a pivot here. Those are the column. And I have, that's the situation. That's the echelon form of A. Does X equal to B has a solution regardless of what B is. Means if I put anything here, so that's AB is equivalent to that. Can I put anything here and generate a solution? Yes or no? Absolutely not, because that's the echelon form. If I take a vector something, 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 1, I can always reverse my operation to create a vector B, which will lead me to that. So does AX equal to B have a solution? No. Absolutely no. There is always a possibility of finding a vector B so that when we solve, we're going to end up with this scenario. So there is no solution in this case. Question number 2. Actually, I'm going to ask the same question, but I'm going to change the matrix. Suppose A is 4x3. Okay. Suppose A is a 3x4 matrix. 3x4 matrix. And A has 3 pivots. As I said, start imagining the problem in your mind. Question number 1. Does the homogeneous system, remember, homogeneous systems are always consistent. So any question about the homogeneous system is going to be, is it unique or infinite? I don't have consistency issue because x equal to 0 is a solution. Does AX equal to 0 has a unique or infinitely many solutions? Draw the matrix is in your head. You see 3x4. It had 3 pivot. Try to have a picture. 3, it means that's the number of rows. And 4 is the column. Okay. And it has it has 3 pivot. It means when you reduce it, so that's the echelon form of A. That's the echelon form. When you reduce, I have 3 pivot. It means since it has 3 pivot and have 3 rows, it means we have definitely a pivot in every row. So that's one scenario. That's not the only scenario. So we can have that scenario. So that's one scenario. We can have other scenario for the echelon form. That's the scenario. So since we have a pivot, so we have 3 pivot. So is it the solution unique or infinite? Since we have so the solution is definitely infinite because since we have 4 columns and 3 pivot, one of the column has no leading. Has no leading. It means the variable that correspond to this column is free. Okay, so in my scenario, X3 will be free. As I said, this is one scenario. The echelon form doesn't have to look exactly like that. We can have a leading here and a zero here, and then X4 will be free. But considering we have 4 column and 3 pivot, it means one of the column has no leading. It means the variable that correspond to this column is absolutely free. Hence, we have infinitely many solutions. Infinitely many solutions. Again, I repeat, I don't have consistency issue because x equal to 0 is a solution. All right, now, does ax equal to b has a solution for every b? Means if I solve the system, a is 3 by 4, whatever a is, and can I plug in anything to the right and have a solution? Does x equal to b have a solution for all b? Again, look at the picture again and ask yourself, is there any way I can create inconsistency in this scenario? Yes or no? Does it have is for all B? Haley said no. Anybody else? Watch your echelon form. That's why I drew it here, and I expect you to do the same. Is it possible to have inconsistency in this scenario? Okay, no. So I mean, I'm getting no and yes. So now we have to be sure. What am I asking? What's the answer to this question? Does Ax equal to B have a solution for all B? I want. So Devlin said yes, and he's absolutely correct. Absolutely, we have a solution for all. And why we have a solution? Because the echelon form has a pivot in every row. It means in this case, when AB is reduced, we cannot have the scenario, have the scenario 0, 0, 0, 0. This is non-zero. Because every row has a pivot in this case. So let us know that in this scenario, every row has a pivot. Every row has a pivot. I have 3 rows and I have 3 pivots. Every row have a pivot. It means that when we reduce, we cannot have the scenario. Hence, AB is consistent. For all B. Okay, so these are the effect, what the coefficient really tell us about the system, what the coefficient tell us about the system. So if you're working with a system, let us say, and your coefficient matrix has a pivot in every row, then you can automatically say that regardless what I plop in here, I'm gonna have a solution. If this doesn't occur, we don't have a pivot in every row, and then, okay, we have an issue. We cannot always solve the system regardless what the right side is. Now, the last thing, I'm going to relate everything we said to the idea of a span. So I'm going to bring the span a little bit into the picture. So this is my problem. This is my question. So, problem, whatever. Okay, I'm going to give you 3 vectors. I'm going to explain what I am going to say. So I'm going to give you the vector A1. So now I'm thinking about span and linear combination and all this stuff. 1, 1, 0. And A2, I'm going to let it be the following vector, 2 minus 1, 3. And A3 is the following vector, 3, 2, 3. Okay, so I have 3 vectors in R3. And my question is, and I have to fully explain my question. If I take all possible linear combination of those vectors, it means when I take the span of them, is all possible linear combination, which is geometrically, I start with A1, stretch it a little bit, move a little bit in the direction of A2, and then move a little bit in the direction of A3. So I take all those linear combinations. Is it possible to hit every vector in R3? It means mathematically we will write, is the span equal R3? What does this mean? Equal R3, so this is all the linear combination. So it means that, what does it means that does every vector B does any vector B in R3 a linear combination of A1, A2, and A3? That's really what it means. Is the span equal R3? Mathematically mean, if you take any vector in here, can you write it as a linear combination of A1, A2, and A3? And, you know, our geometry has limit, so we don't know exactly if it's the case. So we have actually to discuss this. So what does it mean? It means so we take any vector B, and I ask myself the following question, that be here. Question, does the following equation means equal to B has a solution? Okay, so the question is, I take any arbitrary B and ask myself, does this vector equation has solution for all B? Which is, if you realize, very much the problem that I did a minute ago, but in a different perspective. I'm looking at the system in a different way. So if I take any arbitrary vector, can I write it as a linear combination? Okay, I really don't know. I have to solve. So this is equivalent to solve the following system. So this is equivalent to solve this one. B is B1, B2, B3. Now, if I add C1A1 plus C2A2, I will get C1 plus 2C2 plus C33, and I will get C1 minus C2 plus 2C3, and I will get 0 plus 3C2 plus C3. So we've done this before, that's sure of that. So that's equivalent to solve the system, C1 plus 2C2 plus C3 equal B1. Remember, C1, C2, C3 are this weight, so they are my unknown here. C1 minus C2 plus 2C3 equal B2, and 3C2 equal B3. And the question, can I always find solution for the system, regardless what B1, B2, B3? And as you realize, this is exactly what we're doing. So I write this 3B1, 1 minus 1, 2, B2, 0, 3, 3, and B3. And now I solve. And I solve. So what do I get? Did I do this before? I think that's the one I did. No. So I have to solve. And I actually don't know if I can solve it all the time. So 1, 2, 3, B1, minus 1 plus 1, 0. minus 3 plus 2, and minus b1 plus b2. Finally, I will have 0, 3, 3, b3. Okay, I'm gonna go one more step, and I will be at the echelon form, and I can decide. So finally, this is equivalent to 1, 2, 3. That's my b1, 0, minus 3, minus 1, 0, 0, 2, b3. Question. Can I write every vector B as a linear combination of A1, A2, and A3? Can I always find a solution? What can you say? Okay, is this system consistent? So this is consistent regardless for all B. Basically, because if I only look at this matrix A, I have a pivot in every row, so I don't care really what's happening in here. This is consistent for all B because we have A has pivot in every row, which means that every vector B is in the span of the vector A1, A2, A3. Means no matter what I pick for B, I can write it as a combination of the three vectors. So the span is actually equal to R3. Means we can cover the whole space with those linear combination. Okay, so my last question is the following. I'm going to give you vectors, and I'm going to ask you the following question. So question number 2. I'm going to take A1 to be 1, minus 4, 0, and A2 to be 3, 9, minus 3, and A3 to be 1, 3, 2, sorry, minus 6. Okay. And I'm going to give you the following. Suppose A is the matrix whose columns are 1, minus 4, 0, 3, 9, minus 3, 1, 2, minus 6. So that's my matrix A. And so basically my matrix A, this is the A1, this is A2, and this is A3. And I told you that if I reduce this, I get 1, 3, 1, 0, 3, 6, 0, 0, 0. If I reduce it, and the question is, if I take the span of all those vectors, do I get everything in R3? What do you think? Okay. All right, so I want an answer to that. Absolutely not. Answer for Tuesday. I want you to be, all of you, I want you to be able to answer this question for Tuesday. And the answer is obviously not, because I don't have a row in every corner, I can always find a vector for which AB does not have a solution. And these vectors will not be in the span. Okay. All right, for this, I finish the lecture for today. As you guys know, Tuesday you have a quiz 1 and quiz 2. I am hoping to be back in school on Tuesday, so I will give you the quiz. in case something happened and cannot be back, I will email all of you and tell you that I won't be back. But regardless whether I'm back or not, you will have a quiz on Tuesday. It will be quiz 1 and quiz 2. The plan is to be back and the quizzes will be in class. In case I can't, the quizzes will be online. And so we will meet as regular on Tuesday, whether in class or on Brightspace. And if it is in Brightspace, I hope it won't be, you will guys take the quizzes online. Otherwise, if you don't get any message from me, it means school is as regular and I will be in the classroom on Tuesday. Now on Brightspace, I did put like a document with all the topics that we've covered so far. That's to help you to be able to study for your quizzes. Okay, any questions? And please stop by my office hours if you have problems. Okay, any questions from you? All right, bye-bye and see you on Tuesday, hopefully face-to-face. Bye for now.